all right. Okay. Good evening, everyone. Welcome back. And greetings to everyone who are watching us online. ISU SSP Space Studies Program Distinguished Lecture Series number 7. Time flies. We are already almost at the half of our Distinguished Lecture Series. There are more to come, but today we are actually discussing a very interesting topic. But also, before even that, today is a very, very historical day. Yeah, right? This is what you actually see, the first light from the James Webb Space Telescope. So before we go into any discussion, our expert, our guest, our speaker today, Jim Green, will definitely touch onto this because this is today is history, and definitely Jim was part of this effort as much as every other mission he had been part of it. So with that, for everyone joining online, our speaker tonight is Jim Green, the former NASA chief scientist and currently the senior advisor to the Office of Chief Scientist at NASA. And today we are discussing EVAs or spacewalks, and in particular, how do we train astronauts for these spacewalks, particularly the neutral buoyancy simulations. But before that, let's give a warm welcome to Jim, and the stage is yours, Jim.
Thank you. Thank you very much. So indeed, today is a very historic day. You'll probably remember it in the future, at least NASA will, because it culminates in a couple decades worth of work with many thousands of people that have contributed to this mission over extensive time. So we're going to talk about the first light from the James Webb Space Telescope. That happened today. When you were in studies and doing a variety of activities, and so many of you perhaps didn't see it. The person I want to introduce, though, is this gentleman, Joe DiPasquale. And Joe is the person that actually gets the raw data, manages it, and creates the beautiful images you're going to see, because the data is not in the light that our eyes can see. It's not in optical wavelengths. And so I interviewed Joe in Gravity Assist.
In just a few days, we're going to see the first images that came from the James Webb Space Telescope. Let's talk to somebody that's worked to make these beautiful images come to life.
The images are spectacular. They're going to blow people away. There's sort of like a universal appeal to these images. They touch on a collective need or want to understand the deeper questions of the universe that we all have in ways that connect us all together.
Hi, I'm Jim Green, and this is Gravity Assist.
Now, Gravity Assist is a podcast I've run since 2015. And indeed, I've interviewed approximately 100 different individuals and scientists in the field. And I wanted to talk to Joe because there's a lot that goes on in the background to make these images really pop, really come to life. And indeed, that's what he did. So the details on how he did it is in that podcast, and we posted it Friday of last week. So this is the first image that was released. It actually was released last night. President Biden released it in consultation with NASA and the administrator, Senator Nelson. It's a beautiful deep field image. It's called SMACS 0723. When you look at this, you see a couple important things. You see the stars with the diffraction patterns. The secondary mirror is held up by these little things that hold the mirror together, and those produce diffraction and it ends up in the image. Those are stars that are close to us. Those are stars in our galaxy. But just about everything else are billions of years old behind it. This is really an astounding picture because not only do we see these beautiful galaxies, we also see what we call gravitational lensing. So in the very center of this image is a large probably cluster of galaxies that are so massive that as light coming from behind them reaches the space that these galaxies occupy, and that they warp, those light rays then bend around them, and they create these funny circles. You see these circles, just barely, you can barely see multiple ones, and those are probably one or two galaxies for which their light has been split up and then put in this arrangement. And we can put it all back together to see what's behind this massive cluster of galaxies. Now, the real breathtaking beauty of this picture is really in the details. This is a large image, 5 megabytes or more. And if you want to play around with it, open it up and bring it in and look at it. That's really where the beauty is. It's fantastic. Hubble did a deep field look in space, black space. Nobody thought anything was there. Turned the telescope there, studied it for 2 weeks, let photons come in, and saw galaxies. Okay, and that's what Webb does, but Webb can do it so much better because it's got the right wavelength to look at these galaxies. Now, it turns out, if you can remember the electromagnetic spectrum lecture, the angular width in the sky you can see is related by 1.22 with the wavelength and the diameter. Now, Hubble, its wavelength is in the optical. Webb's wavelength is in the infrared, and it's longer, okay? So that means, to mean the same resolution of Hubble, is you have to have a bigger d, which is the diameter. So the resolution by Hubble is about the same as the resolution by Webb, okay? Just because the mirror's bigger doesn't mean you have better resolution. It's really all about the wavelength, which is part of that calculation. Okay? The next one is a spectrum. Webb has so many modes associated with it, and this is just a taste of those modes. A lot of the detail behind what's going on will be scientifically rich. So this kind of gives you what the scientists are going to want. They're going to want a spectrum. Now, a spectrum, of course, is just like we talked about a spectrum of the sun. It's an absorption spectrum. So you see the beautiful continuum, and then you see pieces that are broken out of it, which are emissions, absorption lines, rather, from atoms in the atmosphere. And here's that same concept of a spectrum, but it's a different planet. It's an exoplanet. It's a big one. It's about the size of Jupiter, around a sun-like star. And it's not that far away, 1,000 light years, not that far away. And it's very close to the star. This planet was not made in the position it currently is in. It was moved. These are some of the new concepts that we're realizing in astronomy, that huge, massive planets can actually be moved. And it requires another planet. So somewhere in the evolution of this solar system, these two fought for position. One was thrown out, one was thrown in, and we're looking at the atmosphere of this planet that's very close to the star. It's about the size of Jupiter in physical size, and that's because it's close enough to the close enough to the star that the star has heated up the atmosphere. And we see in the atmosphere water vapor, water vapor, water vapor. So they just made marks where they see the water vapor, and it's there, okay? So this is an emission spectrum where these peaks are the lines that indicate water. Now, there's all kinds of other things in this spectrum that they didn't point out, but the scientists will really tease it out. So we're really excited about these kind of capabilities because we want to look for planets that are about the size of the Earth that have the spectrum of our atmosphere. Okay? Okay, another one that's pretty exciting is the Death Star. This is a planetary nebula. It's actually a binary. And two instruments, one NIRCam and one MIRI, actually made these observations. And these colors represent different aspects of what you're seeing. You know, for instance, the blue colors from the NIRCam are really hydrogen that's being lit up by the star. But it turns out when you take a more detailed look at it, it's a double star. There's two stars here. There's two stars at the center of this. So one of these stars has actually exploded, and what we're looking at is really the layers of that star that are leaving and moving out into space away. And as you can see, it's exploding in nearly all directions. And these colors represent certain aspects of the wavelengths that the scientists really are going to dig into. This is a dead star on its way to its final state. This is really an astoundingly beautiful set of images. It's called the Stephan's Quartet. It's 4 galaxies, but you see 5, right? But the one that I've blown up here is not associated with the other 4. The other 4 are all close together, but the 5th one that sits off to the left is closer to us. It's not affected by the others. They're very different locations, although from our point of view, they look like they're all together. This one, you can even see stars in a galaxy, in this galaxy, far, far away, all right? Really beautiful. And the one at the top, they now believe it has a black hole. So that one will be studied a lot. This is the last one. It's a star-forming region, and this is what I really like this one, because this is where stars are being created, and as they come together, they'll have magnetic fields, and these magnetic fields, like our own sun's magnetic field, produces the heliosphere. These stars will produce an astrosphere, we call it, okay? So we want to take this region apart and look for these astrospheres. And we're going to look at the age of the stars. This is where there's so much material here. Stars are being made all over the place. And when a star gets made and then all of a sudden starts burning hydrogen into helium, it has a wind and then it starts blowing material away. So the top half of this is where new stars have been made and have blown the gas away. And some of that gas now is being blown together, and it of course, is making new stars. What's really spectacular about this, of course, is the detail. You know, this is a huge file, and when you open it up and really peer into it, you see all kinds of structures. So it's really quite beautiful. Now, I'm going to take quick questions and give you quick answers. We'll do a couple, and then I want to talk about what we'd originally scheduled, which of course was scheduled well before NASA announced that on the 12th, this day, we would have the first images from JWST. So anyone have any quick questions? I will mention while the microphone is coming to you that Aaron Young will be here next week, and he will be talking about JWST and give you a much better background. And he is a galactic modelist, and so he models these galaxies that we're looking at. Yes.
Hey. Hear me? In the first image, the deep field one, there is the big thing in the middle, and there are these circles around it, and some of them are quite far from it. Like we see in the end of the image, those circles, while some galaxies quite closer to the middle are in the correct form. How come? Like the first expectation?
That's a galaxy. That's a huge galaxy. There's another one. There's another one. This is a group of a cluster, we call it, of galaxies, and this is producing the large mass for which light behind it is being moved around it.
Yeah, but
and the light around it that's being moved around it appears like this in these little arcs.
So quite a large angular distance from it, and other structures much closer to it seem unaffected.
Yeah, so this galaxy in the center is probably 2 billion years, and you're looking at galaxies behind it that are about 13 billion years old.
Some other galaxies are closer to us.
These are, yeah, this group is closer, and what it's done is it's moved the light from the ones behind it. Okay? Okay. One more question.
Jim, how long do you think it took for them to look at, say, even that image on its own, for them to make the conclusions that they did? If we take even like the star death, to see that and to process it, and then for them to come up with the conclusions, just those top level conclusions.
Yeah, Joe
how much time is in that?
Yeah, Joe takes a couple days to create the colored version. Okay, a couple days. But Webb has been in such good shape that it's actually been taking data over the last 2 weeks. So it's really creating all kinds of data that then is going out to investigators. And so these were the top things that they wanted Webb to do, and not knowing what they would end up looking like until after Joe got done with them. And then, of course, they're just drop dead gorgeous. But now this starts the whole pipeline. Webb hasn't stopped. It's cranking out data. Hubble spent 2 weeks on a deep field. Okay, this is nowhere near that long of an exposure because this happened in the last 2 weeks. Okay, so and then all the other measurements that it's been making. But it's the right wavelength that makes the difference. It's really receiving the right photons, whereas Hubble was receiving fewer of the photons, and therefore took longer. Okay? All right. So let's go ahead and talk about. Okay, one more.
Yeah, hi. Just one question. So if we're looking 13.2 billion years ago,
Yeah.
so it means that we're getting closer to the Big Bang, right? We're like
Yes.
just half billion. So what's the next step? How do we get closer? What do you need to change the wavelength?
Yeah, we change the wavelength. We go into radio, and there's only one place that we can see it, and it's on the far side of the moon. And we talk about that all the time. And so I think the next big step, it's actually the last thing I'm going to talk about tonight, is living and working on the moon. How do we simulate that? Does water take any role in that? And what would we be doing? So I'll just cut to the chase and tell you, we're thinking about building a very large radio telescope on the far side of the moon, and then make the observations that is called the Dark Ages. So right after the Big Bang, we have a place we call Dark Ages, and then we have this era for which JWST is looking at right now. It's the making of the first stars and the first galaxies. So astronomers love to use the word dark. When they don't understand anything, they call it dark. Dark energy, dark matter, dark ages, right? So we got dark ages to go for, and that's in the radio regime, okay? Okay, so let's talk about making spacewalks successful. And how we do that, of course, is we use water. But this idea really took a little time to mature, but then it rapidly exploded in terms of what we did. So I'm going to talk a little bit about what EVAs are, extra-vehicular activities, give you the basics. We'll talk about the history of the neutral buoyancy efforts, in particular one tank that NASA put together that they used for a significant period of time. And now they're everywhere. About every agency's got one, okay? And then how do we do that? How can we go into what could be thought of as a more risky environment to then mitigate risk in space? Scuba diving requires training. It's not natural to us. So there's all kinds of diving support personnel that are needed. And then how do we do it? Well, we're going to use real spacesuits. And then we're going to talk about major events that have happened in the past, several in particular that are really astounding, and how we really solved some of the problems we needed to here on the ground in a tank of water before we went to space. And then we'll talk about some of these future ideas. Well, many of you know that human exploration has major advantages. And for me, this is just a few of them. Situational awareness, the ability to communicate in human language quickly, dexterity and adaptable dexterity, okay, learning to do new things. Pattern recognition, they can expect the unexpected and then react appropriately. Human anticipation, and they're involved in upgrading, repairing, and of course, figuring out a way to survive. Now, extra-vehicular activities, or EVAs, really boil down to anytime a crew member is no longer protected by their home vehicle and they're exposed to the space environment. So that means they put a suit on and go outside. They are literally a spacecraft themselves, okay? They have their own environment with them, and that they have to maintain that, keep that, and then they can live and work in that environment, but only for a glimpse of time. Now, we've gotten better in terms of extending the length of that over time, but you have to have the right pressure, breathable atmosphere, thermal control, mobility, visibility. You need to communicate, and you need protection from some of the harsh environment. And spacesuits do that. NASA considers EVA activities as one of the top 3 risk events in human spaceflight, okay? And so we treat it very as such, and we work hard in mitigating those risks and then make decisions on what we're going to do based on the best way to do it. Now, what really boils down to what we're trying to solve is we want to be able to do things in space, and we have to do them quickly. We can't just stay in space for long periods of time and work it out. There's fatigue, there's other issues that occur, and as soon as you push the limits of a human in a working environment like this, you then have higher risks associated with it, with decisions that can be bad. So you really, operationally, you want to be as efficient as possible. You want to be able to figure out what you need to do, figure out what the steps are in the processes to do it, go do it, learn how that works over and over again until you can do it in your sleep, and then go out and do it and get back in, okay? And then you're going to find you're going to be successful most of the time. We now are in the position where we do these EVAs with buddies. And that's important, okay? And you'll see also that as one dives in a neutral buoyancy tank, we do them with buddies. So the origin of this really started in the 60s. There were quite a number of engineers at Marshall Space Flight Center that were thinking ahead, all right, and figuring out that, look, we're going to be developing space stations. We're going to be, working outside in and along after the shuttle comes out. There's a number of things that we're going to need to do. So how are we going to mitigate that risk by practicing it on Earth? And so many of these engineers took a Saturn, not a complete stage, but an element of a stage, buried in the ground, filled it with water, jumped in, and started performing procedures like they would in space, okay? And that gave them the idea that, indeed, neutral buoyancy might be the best way to go. So by February 1967, NASA headquarters approved one of NASA's centers, Marshall Space Flight Center, to do a variety of things in the neutral buoyancy simulations in a tank of water. And those things were the following: provide engineers an opportunity to develop tools. All right, when you think about it, you can't take a screwdriver and expect it to work, or a wrench. things that it's very common for us to do that is really hard to do in space. Well, why? Well, you put the gloves on and you pump up the suit, and it's at 3 pounds per square inch of pressure above the ambient. And so your fingers go like this. And so now you have to move your fingers against this pressure. And that's fatigue. And now you have to grasp something. Find things, small screws and D connectors. I mean, I can hardly do that at home if I want to do some if I had a spacesuit on, with puffy gloves. And so tools had to be invented, new tools, to be able to do these tasks quickly. And then simulate this weightless environment such you can develop a procedure. You build new equipment, you want to test it out. You put the engineer that developed it in a tank of water, see if it works, pull it out, redo it, go iterate on that until it's ready to have an astronaut do it. And then you fly those astronauts in from Johnson Space Center, and they go in the tank, and the procedures are already worked out. They just memorize the procedures, and they do it over and over and over again until it works. Now, sometimes some things require even astronauts to be part of that engineering team. And as we'll see, that happened on several of these teams. So this Neutral Buoyancy Simulator tank at Marshall Space Flight Center, starting in '67, actually was on the design board. They were thinking about this for quite a while and actually had a great design earlier. It was constructed in a year and got it up and running. And the first thing that we're going to do was practice things to maintain the first space station that NASA had called Skylab. It was just all about maintaining it, all about going and doing some EVAs and checking on things and etc. And so consequently, that was the first thing that wanted to do in the tank. Pardon me. Even though Skylab was on the drawing boards, not really completely built and let alone launched in operation, they were already thinking about how to do that in a water tank. That was their first one. Now it's on the landmark, National Historic Landmarks in '86, but the facility was closed down in '97, and a new one was built at Johnson Space Center, closer to the astronauts. Here's the facility, NASA's first facility. It's a huge tank, and it has all the right elements, though. Here's where the experiments will be done. At top are all the basic control center necessary for a suited subject to come up and be plugged into an air supply. So the air comes from the top of the tank down to the astronaut, along with communication, along with a fluid that circulates through a set of underwear that keeps the individual cool. And then everything is all tested out up here before they go in the water. And then you have a control center in the back. And indeed, everyone that is conducting the test sits in the control center. Other characteristics of the tank are that it's large, 43 feet deep, 70 feet in diameter, 1.3 million gallons, and it's a bathtub. It's great. And I have been in it. I dove at Marshall Space Flight Center, 150 dives from 1981 to 1985. And so if you look sharp, you might see me in a couple of these, all right? It has airlocks. It has mounted cameras inside there. It has a mock-up of the shuttle bay, audio speakers that are submerged, and a Canadian arm. And it has cranes to raise and lower equipment. It has a recompression chamber. So if there's a diving accident, you can actually put somebody in a recompression chamber. And then, of course, it has all the scuba equipment and monitoring systems necessary to make this work. So here's some real pictures of the tank. Very tall. It's three big stories. And it's got portholes. which are fun because sometimes there will be tours going by, and if you're in the tank, you'll see kids there, and they'll be waving, and they'll be doing all kinds of stuff. And of course, you've got other responsibilities you're working on, but it's fun. On the top is where you get your scuba tanks, and you get ready, and you work from there, bringing the suited subject down and get them ready, put them on station that they need to do. This is the control center. This looks just like, an old Houston Apollo control group, right? So these are monitoring temperatures and pressures in the suit, as much vitals as they've decided they needed to for each of the suited subjects. And then test conductors are going through the procedures to make sure they're operating. And then all the views in the tank are shown. Now, how they do that is like if this room was full of water, the cameras are then pointed in, and they have their own screens. And then you also have mobile cameras that are there. So the suits they used changed over time. It started with Apollo. These are one-piece suits. There's a zipper that comes around and up the back. You peel it off, and you just dive into it. You put your feet in first, and then dive in the other part, come up, and then zip it up. So the zipper goes around here and up. And here's the underwear you put on first. And this has tubing. There's tubing everywhere here. And so fluid circulates through here and keeps you cool. Real essential, because you can get very hot in these suits. That makes it really wonderful to environment to work in. Shuttle suits came along. It has still the cooling underwear, but you also had modular systems, arms, torsos, legs, which was great, because if the Apollo suits were made for individual astronauts. So when I went into the tank, and I did this on one occasion, I wore Jack Lausma's suit. And Jack Lausma's suit, his arms came right up to here, and I had a glove that came up to here, and I wasn't going to get out of this suit because I wanted to get in the tank. So I had to go like this and work in the tank like this because the suit didn't fit me. But that was the biggest suit they had, okay? And that was great. And I was able to perform a few things during that one test. So that was successful. So the shuttle suits have been really wonderful. They're layered, okay? They're just like they use in space. So one of the mantras NASA has is you test as you fly. So you're going to be in a real suit. And what's interesting about these suits is you think if you're in space, all your air supply is there and it's all tightly put together and it doesn't leak. And that's wrong. These suits leak. They're designed to leak. They're designed to leak because it's too expensive to make them airtight, okay? It just works better. Now then, you just supply them more oxygen, okay, and you let them leak. Now, if you put a suited subject in the water, they need to be watched. And the people that can touch the suit are called the safety divers. And there's two of them. One that puts weights on the suited subject, and the other that mines the air supply. And so that's not only air supply, but it's also the fluid to keep them cool. It's also the electrical system so that they can communicate back and forth sound-wise. And so that's what the second diver does. Now, what about this weight system? Well, as I mentioned, each suit is like 3 pounds per square inch. So if you put somebody in a suit and you throw them in the tank, you're going to float like a balloon, right? So what you have to do is you have to put about 150 pounds on them to drop them. And then you've got to put a distribution of weights around their arms, their thighs, their back, their chest, their legs, their ankles. And that distribution of weights have got to be so perfectly done that you can pick them up and put them in any orientation you want and let them go, and they'd stay there. That means their feet don't go up, they don't roll over, they don't lean to one side, because that means the weight distribution isn't working for you. And for safety divers to be able to do this, the requirement was that the person that puts on the weights and weights each individual suited subject out has 3 minutes to do it. Because any longer, you're just wasting everyone's time, okay? And I was a safety diver that could do that. And part of that was because of my height. I was able to just take whoever's in the suit and just move where I wanted to and get to places that needed the weights. So my height was an advantage. We also have utility divers. They're the ones that bring in the equipment. The wrenches, making sure things are there. We'll set up the initial foot restraints. But once you put, once a safety diver puts their suited subject in foot restraints, they are the only ones that can touch the suit. They are the only ones then that can move that foot restraint, unless the suited subject gets out, and then the utility diver can go in. So no one touches the suit except those two safety divers. Then we have water safety. These are really important people. And the reason why is when you dive, you always have a buddy, okay? For those that have dove, this is very important because if you get in trouble, your buddy is there. But if the two of us safety divers were buddies and I got in trouble and my other safety diver tried to help me, who's watching the person in the suit? The number one thing that we were there for, right? And so my buddy is swimming on the top of the tank looking down at me, and he's the water safety, or she. And so whenever I needed to be replaced for whatever reason, all I needed to do was look up, go like that, they'd come down, replace me in a second, and I would leave, and the suited subject was always tended by two people. 4 eyeballs were looking on everything they were doing. That's water safety. Then you had cameras, both a video one, but also still cameras. And then the test conductors were way in the back. And then sometimes you'd have non-divers that would be observers. And then a chart like this was always filled out, okay? And this turns out to be one that was done for one of the Skylab dives, and it's got Story Musgrave on it, and so you'd come in to do some work. Okay, so you suit up at the top of the tank. Here is a full Apollo suit, all set. Snoopy cap has to be very tight so it doesn't roll around. All right, and then you can see the weights. This is a pack of weights, 2 packs of weights here. Here's the thigh weights. Here's the ankle weights. And then a very large backpack will be placed on your back, and then you're taken down. So you're taken down right here after you put the backpack on, down to about a 15-foot level right here. And then here's the second safety diver minding the umbilical, and here's the first diver, waiting them out. Okay, and you can see you just sit in the suit and they just throw you around. They're constantly throwing you around. They're trying to get to where they need to be to put the weights in the right place. And you might be fun, but at the end of that, you better be weighted out. And then when you're done, the safety diver puts his thumb up, and one of the people in the camera sees it. Then the test starts. You take them down to do the work they're going to do. Now, I've gone into this because I know this is one of the activity to this level, because I know this is one of the activities that are going to be talked about in the engineering department. Okay, so here's some basic level information of how NASA does these kind of things. So let's talk about some really great events. Skylab. All right, so one of the first Skylab dives and one of the first Skylab divers in a suit was Werner von Braun. And this was when we developed hardware. Marshall Space Flight Center did in 1968. The first thing in the tank was a wonderful mock-up of Skylab. And here it is. This is a fabulous solar telescope, the Apollo telescope. It's right here, Apollo telescope mount, and the mock-up had all these kind of activities, and several astronauts would come and work in this environment and get a feel for what it was like. Okay, and then you see some of the support divers there. But what happened, even though they were practicing things since 1968 when the tank came in, getting ready to go to Skylab, thinking it would be just normal outside repairs, is the problem with the launch. It started right away, that after about 60 some odd seconds, there was a premature deployment of a meteoric protection shield, which was actually ripped off. So here's the whole Skylab that fit at the top of a Saturn V, and as it got close to orbit, it then jettisoned this, and then a whole series of normally controlled actions occurred, and one thing went wrong right after another. Another part of it was the solar array. One of them didn't deploy. So that meant the crew, which was going up in the next launch, didn't go up because they didn't exactly know what they had. There was a lot of people that were saying at the time, oh, we goofed that up. Let's ditch this thing and do it again, okay? And of course, that's crazy. I mean, that's let me not say it that way, because that wasn't my idea. It doesn't mean it's crazy. But the agency decided not to do that. And one of the main reasons not to do that is we have a facility that we can go right to and start developing the processes and procedures to fix it. Why aren't, let's use it. No, this happened on May 14th, okay? Okay, May 14th. All right, so now the crew that were going to go up were delayed. So everyone turned to the neutral buoyancy tank to work it out, and they did. They figured out how to use the right tools to unjam the solar array. They figured out they needed to shade the temperature inside. The Skylab was way too high, and so they figured out how to do that. And here's a mock-up of some of the things that they were doing. And not only were the engineers in there, but many of the astronauts would come and do that, like Rusty Schweigert. Now, Rusty didn't end up being a Skylab astronaut, okay? But he was so knowledgeable about EVAs and so knowledgeable about how the astronauts would work, he bridged that gap, and so he was a really great resource for the engineers to talk to. Okay, and so here's some of the tie-down systems they had to put up to get the solar system or shade rather working. And here's two other, there's Rusty and Gibbons working on these things. So here's Rusty in the tank repairing the jam solar array, and here's how it actually happened with Kerwin and Conrad. So once the procedures were worked out in the tank, the real astronauts that were going to go up now can go up, and that was Kerwin and Conrad, and then they went in the tank and learned the procedures, memorized them, okay? This is what we got to do, and then they took off and went and did it. What's really phenomenal is that repair mission took off on May 23rd, okay? Such an incredibly short period of time, but incredibly intense work in the tank to not only understand what the problems are, but work around the engineering solutions, cut metal, be prepared to deploy things, tie things down, make sure you have the right equipment. Do you need a crowbar, or do you need, a smaller leverage system? What do you need to do some of these things? And they worked it out. And they fixed it. It's remarkable. And in fact, Conrad said, mobility around here is super. Every kid in the United States would have a blast up here. Yeah. And so that success, continued. Skylab 3, Bean, Garrett, and Lausma, and Skylab 4, Carr, Gibson, and Poe also went up. And the days in space then began to increase. what was phenomenal about Skylab, not only our first space station, was the tremendous science that it did. And we don't talk about it much, but it really, the telescope looked at the sun in soft X-rays, ultraviolet, and visible light. The visible light's good. We see it here on the ground. Visible light is what then we can easily see in space, but the others we can't. The others we hadn't before. And so here is a way that we could really look at the sun like we've never done before. Now, one of the experiments was also a coronagraph. The very first time we flew a coronagraph, which is block out the light of the sun and see the scattered light. Now, they thought at the time that the scattered light, we'd see some things, but it would be largely benign until they started seeing these coronal mass ejections blasting away from the sun, like I showed you on Friday. That's what they were seeing. Shocked them, all right? Why didn't we know about that? That's what they look like in real life, in tremendous science. They grew crystals. They did all kinds of earth science observations. Really helped pioneer some of the next thinking of what we wanted to do, not only robotically, but what we were going to do on space station, the next generation. Now, we didn't have the system on Skylab to boost it, all right, in case space weather came along and the atmosphere grew and the drag occurred and they would go down and then re-enter, okay? And the concept was we'll get the shuttle done in time and the shuttle will go up and boost it. Didn't happen. Didn't happen. NASA learned a really tough lesson. We didn't know really enough about space weather. We recognized it was a problem, but it really came home. If you look at the number of satellites that re-enter, you plot the number of satellites that re-enter over time, you get this sinusoidal curve, and you put the solar cycle right on top of it. And the reason why is during solar maximum, the X-rays and ultraviolet light from the sun, which we didn't see from the ground, but now when we look at it, we see the immense UV and X-ray emissions that happen during solar maximum really pick up, heats our atmosphere, and moves that and our ionosphere up, causing the drag to bring anything down. Okay, so we talk a lot about orbital debris, things that humans put in there. What we need is a real good solar cycle and sweep it all out. And that happens during solar maximum. Or we need a Carrington event, right? That's okay. So we couldn't get the shuttle up and running. It was several years beyond that, and it came in July 79. Okay. Well, let me talk a little bit about space station. So the tank is big enough to put a mock-up of the space station shuttle, rather, bay. You know, the entire bay can fit there. This is fantastic. It's full fidelity. You know, you can put pallets there. You can put experiments. You can do all kinds of stuff. And you can see the divers are getting ready for a test. And then, of course, there was always the measure of a good diver, and that's your ability to blow rings of air. The nice ones are really well known by other divers. And then, of course, in these environments, you can begin to create structures. So the concept of how we put space station together and what's the framework and how are modules going to fit together and how are the solar panels going to fit, and some of the engineering then is done. And here's probably one of the shortest divers ever, or suited subjects ever. This is a university professor from MIT, and I was just delighted she was tall enough in the smallest suit to be able to at least look out. And there she is, and she did great. We worked with a variety of universities to be able to look at these structures and build things. Okay. One of the most spectacular missions that I actually had a privilege to be involved in is this one. This one, I guarantee you don't know anything about it, and it's probably one of the most exciting missions I have ever seen in my entire career. And it's the Solar Maximum mission. And if we did this mission today, everyone would be knowing about it and talking about it. Okay? So what am I talking about? Here's a beautiful satellite launched in February 1980, and in about 10 months, it had a major failure, lost attitude control. And of course, the concept is, can we repair it? And indeed, the concept was executed, and it was repaired and then put back into service until '89 when it re-entered the atmosphere. So that's the overview. Okay. So what really happened? Well, this is a follow-on to Skylab. It was looking at the sun and various wavelengths, doing a fantastic job, and it was decided that we were going to repair it. All right. Now, it was also, like Hubble, designed to be repaired. It actually had a grappling system associated with it. Okay. So it could be captured, brought in the shuttle bay, and repaired. Okay. And so the mission that did it, STS-41C, was launched in '84. It's the first mission to repair a satellite. Okay. This is the first mission to repair a satellite. And they had to replace this huge system, 500-pound attitude control system that was really connected in there. And they had to really find the right procedures, but develop brand new tools to do this. And they had to replace the main electronics for the chronograph and the polarimeter instrument, along with other repairs. It's also the first mission of the Challenger. It's also the first mission of the manned maneuvering unit and the remote manipulator system, okay, which is the Canadian arm, okay. Whole bunch of firsts, okay. Remember when we were talking, I've mentioned this to several, when Curiosity landed, that needed 10 miracles, okay. Okay, this is sort of like that, where there are all these things they all had to work. We're using them for the first time. And so they immediately went to the neutral buoyancy tank to test all these things out. Now, the manned maneuvering unit, okay. So I'm sure, let me just test. Is there anyone in here who has not seen Gravity? Really? Okay. Okay. Your task this weekend is to watch 2 movies, Gravity, and therefore you probably haven't seen The Martian either. So make sure you see those. All right, we're reading the books. Okay. So the manned maneuvering unit is highlighted in Gravity, and it's all about putting a backpack on so that you, in a spacesuit, which is like a spacecraft we mentioned, have mobility to do all kinds of stuff. I mean, you have the mobility to get in so much trouble, it's unbelievable, right? And indeed, this is pretty phenomenal system. So the decision was made that we needed this MMU to capture the spacecraft and bring it over to the shuttle so it could be repaired. All right. So this was a very essential part of the whole system. Here's the tank version of the MMU. Okay. Here's the tank version. And although we had some problems, it really is a pretty spectacular system. You can go up, you can go down, you can pirouette, you can go right, you can go left. And these little motors allow you to do that with hand controls on these bars that you rest your arms on, that you just scoot around. I mean, they're just really phenomenal. And then here's a full fidelity solar maximum mission in the shuttle bay as if it was captured. And then the mobility used here, okay, and so this is some of the imaging that was done. So a lot of testing was going on. So these are just beautiful views that I'll just go through. Now it turns out some of these panels weren't meant to be opened up as if they were going to be repaired. So we learned a lot on this spacecraft that we changed when we did Hubble. We made Hubble easier to repair, okay, even though this was supposed to be repaired. But what that did mean is we had to develop a whole series of new tools. So this is a really great tool. It's a hex nut driver, and it takes advantage of the fact that you only need to move like this. Put your hand on the rotor and then turn it, okay? And really have fine motor skills when you do that. And all kinds of tools like that were made. each of these little things here have these little bitty screws, like these are called D connectors. They all have to be disconnected. This whole unit had to be pulled out and replaced, and then all that stuff had to be put back in. And that's astronaut Nelson, and he'll be performing it in space. George Nelson. Yep. So there he is in another view. So we have Scobie, Nelson, Van Hoffen, Hart, and Crippen, okay, who flew in the first shuttle ever. And Crippen was the commander. So why did they decide the MMU was essential? Because SMM is spinning. And to catch it, you need a system to start running around the spacecraft at the rate that it's spinning and then gradually move inward. Okay? Really gutsy. Here's the end effector. So this is the female unit. This is the grappling system. This is the male unit. This is sitting on SMM, designed to be captured and then taken over to the shuttle. So indeed, Pinky Nelson takes off, runs around, connects to the spacecraft, gets right up there, and is trying to connect the grappling system with the female unit he has, and it doesn't work. So he tries multiple times. And apparently, from the time it was launched, it was modified, and the design didn't get updated. So the female unit was developed. Yep, you're right. The female unit was developed with the old system in mind, and now you can't connect to it. So he's going to do everything he can to slow it down. So he's now using his jets to slow this thing down. So here's a spacecraft spinning and an astronaut connected to it that's literally fighting this system. And all of a sudden, the spacecraft starts to nutate. Okay? I mean, this could be total bad news. Total bad news. And just a spectacular set of things are going on. So fortunately, what happens is he does slow it down enough that then Crippen decides, hey, I'm just going to take the shuttle, fly it right over there, and we're going to take the arm and connect to it. Another system that hasn't been used before, right? What are we talking about here? Another miracle. So Crippen takes a brand new shuttle over to a spacecraft that's just barely stable, that's spinning and nutating like this, okay? And he takes the arm, reaches in there, bam, hits it, connects it. And in fact, he was told something about this I don't quite remember, but he really pushed the envelope of the orders he was giving, and he was only going to be able to do this maybe one time, and he did pull it off. Put it in the bay, and off they go. And they repaired it and put it back. After 2 EVAs, they got it up and running, and those EVAs and the processes and procedures were all done in the neutral buoyancy tank. Okay, let's talk quickly about Hubble. Now, the rest of these are so much easier. And the reason why is now we know if we make design changes, we put it on the design, CAD-CAM system and update everything. But what's really interesting is the Hubble had always sort of been talked about being repaired. Now, it launched in the 90s, and here in 1979, we're practicing exchanging instruments in the Hubble Space Telescope, okay? I mean, so, here's another one. In 1970, here's another one. We're doing all kinds of things, and even the astronauts would fly in and try some things. I mean, here's, 1980. 1985, I participated even in a whole bunch of diving on Hubble Space Telescope before it was even launched. So this provided a huge background on as they were building it, on what to do and what not to do, taking lessons learned from SMM, getting the drawings right, making sure that if it was going to be repaired, you were ready to repair it. And then they launched it in 1990. This is their first light. And thank God you didn't see anything like that from JWST, right? Well, the mirror was ground incorrectly, the primary mirror. And so the cutting to the chase, everyone knows that we corrected that. And here's the real image that it should have taken. And it was corrected by not doing anything with the primary, but changing the secondary. Really neat idea. Really neat idea. Some engineer came up with that. I know who it was. And they told me they were just thinking about it all day, all night, and couldn't stand it anymore. Went in the shower and thought, oh, well, shit, that's what we ought to do. We just change the form of the secondary and make up for it. That was brilliant, you know? And indeed, that's what they did. Then they practiced it. And, you know, updating the instruments, getting everything, and just did, you know, fantastic things. The astronauts would come in, and indeed, finally, a shuttle was targeted STS-61 to be the first repair mission for Hubble. And here's Jeff Hoffman. Yay, Jeff, go for it. And indeed, and he's in this one too, I believe. And indeed, and he's in this one too. They did it. So STS-61 went up with Story Musgrave and Jeff performing the EVAs, bringing in the Hubble Space Telescope, and then making the repairs necessary, changing out the secondary and many of the instruments, and got it up and running. And since then, it was serviced. Second servicing mission, third servicing mission, and fourth servicing mission. Okay? Well, what about the International Space Station? Well, in a similar way, as you already see, even though this thing didn't go up and get assembled, although it's been operational for the last 20 years until the 90s, they were working on it 15 years earlier. So here's a whole series of different designs and hatches and things they would test in the tank. And then that would lead to design changes, which then would go into actually the final system that they would go up and launch. So really a number of spectacular dives that were done just to be able to make these things happen. And of course, even some of the modules. This is a Jackson module that were tested in the neutral buoyancy tank. Well, let me end because I want to have much more time for questions, and I don't want anyone to be late. And it's hot in here, as we all know. Future missions, what are we doing? Well, we're going to the moon, right? With the Artemis program. We don't need a tank of water, do we? Well, maybe we do. And so now new techniques and new thinking is coming about. This is the tank at JSC, Johnson Space Center, where they're going to be doing a number of things at not Earth gravity, but more lunar gravity, and then try those over time. Okay? And so that's really the way to go. Thanks so much. That's a little overview of how NASA has used water. The technique is all over the place. Many of the major space agencies have their own tanks that does indeed simulate how we work in space such that we can actually take lower risks when we do EVAs. Thank you much.
Hello. Thank you for the whole talk. It was really cool. My question is, I know there's been like redesigns of the spacesuits, and there's other, I think, I don't know too much about the new spacesuits or what's being designed for Artemis, but has that been easier or harder to work with as far as for the Neutral Buoyancy Lab?
Ooh, good question. Yeah, the new Artemis spacesuit has been announced. It's been shown. I don't know if it's ever been in the Johnson tank. It may have been. Sonny, do you know if they ever put the new suit in the tank? Is the new Artemis suit ever been in the wet facility, the NBL?
Yeah, I don't know if it's been in the NBL. I know now that they're changing over to a new contractor for the suit, those suits will definitely be in the NBL.
Ah.
Are you guys aware that the new suits are being contracted out?
No, they were just wondering how the testing was going for the new suits.
Yeah, so we just had a new contract come out I guess it's been a month, maybe 2 now. NASA themselves are no longer designing the new spacesuits for EVAs. We are contracting that out to 2 companies. I cannot remember either one's name. Jim, do you know? Is Axiom one of them? There you go, Melody. Thank you. Axiom's one of them.
Wow.
Do you know who the other one is? Oh, of course you don't. It's a competitor.
It's a competitor. Yeah. Right. Thank you. A couple other questions. We have one here, one there. Okay. Okay.
Yeah. Hi, Jim. Thanks for the amazing presentation.
Sure.
Two questions. First of all, having divers to put weights into the suit to neutralize buoyancy sounds like really low tech. Don't you have like a mechanized system to do this? Or haven't you thought? Or why not? And
you were a classic engineer.
I'm sorry. My apologies.
No, that's
second, you by the end of your presentation, you spoke about simulating moon's gravity.
Mm-hmm.
But there, I believe that the resistance, the viscosity of the water would.
Yeah, let's talk a little bit about the differences between real space and the water. There are, obviously. So in space, your inner ear doesn't function like it does here on Earth. So the fluid in your ear, Tara talked about this, fluid in your ear goes everywhere, okay? So when you're here on Earth, the fluid goes down, and you know that when you move, the fluid moves, the little hairs tell you, okay, right yourself. In space, you mentally have to adjust, okay? Now, and therefore, whatever orientation you're in, this is always up and this is always down because your mind tells you that, no matter what it looks like. Okay, the Earth could be here or the Earth could be there, and that's up and that's down. Yeah. So several of these you saw the suited subject laying on their side working because that's what they'd have to do in space. So the inner ear does tell you you're up or down, okay, in the water. So that's a big difference. The other difference, of course, is, as you pointed out, resistance when you move things. So when they move some of these instruments, as I showed you, that they were replacing in the Hubble, they are actually have floats on the interior. They make them as easy to move as possible. And then the utility divers sometimes get involved to make them also as light as possible, so that you get the feel of the move. But if you're going to be moving rods like they did in a couple of the experiments that the MIT people did, building structures, that produces a lot of resistance. You just have to know that those are going to be the two basic things you're going to encounter that will be different. Okay, we have another question.
Yeah, I'm asking a question right now. Thank you for the awesome presentation. I have 2 questions. I'm here. Yeah, I have 2 questions. One is the Canadarm, which was flown on this shuttle, was it also tested under the neutral buoyancy facility?
Yeah. So we had a Canadian arm there. We had a mock-up of it. I don't know who built it. Maybe the Canadians.
So that was also tested for 0G in the neutral buoyancy facility.
Yeah, it was weighted out such that I didn't show how they operated it, but they actually operated it from outside the tank in a little window in with a control system. So they looked in and then moved the arm around and did the things that they would have done normally from inside the shuttle.
Okay. And the second question is regarding the SMM mission you were talking about. In that you had said the MMU, the person inside the MMU had brought in the arm and connected it to a tumbling target. So does that not create any reaction forces, because both are in free flight, so it is bound to create some reaction forces on the arm. So
yeah, he was struggling. I mean, you're right. As he was hitting the spacecraft with the end effector to try to get it to connect, it was pushing back on him. Well, he had a system he could go back in. I mean, that dynamic, we don't know much about. He does, and he's still alive. He hasn't written his memoirs yet. It would be wonderful for him to do that.
Okay.
But that was a real struggle. I mean,
Okay.
it must have been really exciting to do.
Thank you. Thank you.
But once again, hardly anyone knows about it. When we were diving on that, and of course things were working right because we thought they would work right in space. I thought, man, this is crazy. This is unbelievable, and we're going to do this in space, and then it was only worse. Yes.
Okay. Hi, Jim. Regarding the viscosity that we were discussing and the weights that you can add on, we've been using water to pretend that we are in microgravity, right?
Yeah.
What are the procedures that they are testing out to be different on the moon? Because I think not only we could just like move around, mess around with the viscosity of the liquids we use, right, on the tank. I don't know if there are other liquids that are being tested for trying to produce a differential gravity on the moon. But also if there are rocks that are being used to like differentiate the weights of the things you are trying to move.
Yeah, good question. They have tried a few of those things in the Johnson facility, which is called the Neutral Buoyancy Laboratory, NBL. And I have not visited it or seen them. I've only heard about them. But I think that's the start of many tests they're going to be performing over time and working out some of those procedures. I don't have the details to tell you. Oh, Sunny Mike.
Hey, Jim, could you talk a little bit about any lessons learned from using the NBL? I was thinking of the Leland Melvin incident.
Yeah. So what of course we found using the Neutral Buoyancy Simulator at Marshall is that it really provided a significant fidelity that we needed to be able to represent what was going to happen in space, with a few exceptions that we talked about. But that's not a lot of exceptions. The astronauts got basically the look and the feel. They could adjust their foot restraints. They could work in that environment, and it turns out some astronauts are better than others doing some of this. Okay? And you only find that out when you're in the tank. You want to find it out there rather than on orbit. Now, no astronaut wants to have a part of a job that they don't complete, but if they know they're having trouble, but someone else can do that part of it better, that's the person that needs to do it, because then you want to overall lower the amount of time you're in space, which overall lowers the risk to each and every one of the individual and gets the job done. So you want to do it as efficient as possible, and practicing it in the tank is the way to do it. This is why the astronauts that are actually going to fly and do it only fly in and memorize the procedures that they have all worked out, they know that will work. You do this step first, then this step, then this step, then this step. There's a logical sequence, and it's been worked out that way. So the tank provides a really marvelous way of doing that.
Hi, thanks for the amazing lecture. Two quick questions. One, in terms of diving, does the training that you do are same duration as in space? Because I know from diving that there are limitations to how long you can stay underwater and stuff like this. So this is the first question. And the other one is about like going into the future. How does NASA look at AR or VR in order to simulate some of these missions?
Yeah, right.
And is that a replacement at all or not?
Good question. I don't know about that. We'll see what the future, the future will be. But the divers that are selected to be in the tank are already really proficient. So when they needed divers, and I was at Marshall Space Flight Center, and then I knew about the tank, as soon as that announcement came up, I signed up. And they tested us a little bit, looked at our background and our certification. Well, I had been diving a lot at the University of Iowa. I dove quarries, I dove lakes. I dove in stuff that 4 inches of visibility. I mean, I drove some really crappy stuff. And I ended up being the University of Iowa Scuba Club president. I mean, I did all kinds of stuff. organized rescues to get people out of quarries and, that drowned, some tough stuff. I didn't do that, but I knew divers that did, and we got them together. And, so I had quite a bit of background. And so in my test that they did was only a couple things, and I got selected. And they had like 60 or 70 people apply. They took about 10 of us. And then, of course, I had 1 month of training to be a safety diver. And I needed that to be able to really understand how to do the weights and be able to weight somebody out in 3 minutes and get them ready to go. Now, the other thing is we all had certain things to wear with names on it. So my name, green was on my dive shirt, so that when they looked at us, they could say, "Green, take him over and do this." Okay. Now, I don't have any communication. That communication is done in a speaker that's dumped in the tank. So what's in the tank, water, moves noise very nicely, and so we just listen to the chatter between the controller and the astronaut, and then we listen for our name. So we learned how to skip breathe. Because when you blow bubbles, when you exhale, that goes by the ears, and if they're talking, you're not going to hear them. You're just not going to hear them. So there's little techniques like that you learn to do. So you're always on your guard. I always looked for things, and what was happening, and then I would make some adjustments. Now it turns out during the dive, I would have to pull some weights, okay, because the person in the suit would get heavier. Now, how could that be? Well, the Apollo suits in particular are like 23 layers, and water is seeping in. And if the suit doesn't fit just right, like they are in a suit where they have not as long a legs, you get elephant legs, where the water is sitting inside there. That makes them heavier. So while they try to do a few things, and you can notice it, you go over there and pop a couple weights. And you just let them lay there, because that's not important to us. And the utility diver will pick them up and then move them to where we'll use them the next day. But one time we had a 2-suit dive for which one of the subjects, I had plenty of time to play around, and he was in a suit that just hardly fit. I mean, worse than the little gal from MIT that could hardly fit in at all. We could have put 2 of her in that suit, turns out. And so I took the individual off to the side, on the other side of the pallet. So we actually had, you didn't see it in the one image of the shuttle bay, but we actually had the tops of the shuttle bay open up, and they had these wings. And so I just took him out and took him over to the wing and tried to trim him out a little bit by moving him around and seeing that. All of a sudden, the control people are going crazy. And they're going, "Oh my God, Green, we're going to have to do a decompression." Now, the reason why is the wings were such that he was at a lower depth, okay, than what we typically are in the shuttle bay, okay, combined to the fact that he is in a suit where there's 3 pounds per square inch more pressure on his body than there is outside him. He actually is at a deeper depth than I am, okay? And so a new thing happened in the tank, thanks to Jim Green, and that was now we had to go through decompression for this guy, okay? So they brought out their dive tables, and they say, "Okay, take him out, put him over here, hold him against this part of the ladder, at the 3rd rung or whatever it is, and we're going to wait there 10 minutes. Now move him up another, 10 feet, and then we finally got him out." And I didn't get chewed out over that, but of course that was, it ended his test early. But we typically would dive a couple hours. And at the end of 2 hours, I was really cold. Now, I'll tell you one other thing that I did, that I did intentionally. Okay, so should we turn the camera off? Okay, so this is kind of a fun thing. We're in the tank 2 hours. and and we're handling the suited subject. And if I ever got in trouble, my buddy is up there, right? Now he should be looking at me. Is he going to look at me for 2 hours? Okay. He will if he knows that somewhere in the dive I will look up and I'll go like this, because I'll go to the bathroom. So I always had a lot of coffee before I got in the tank, so that sometime during the dive I would have to go to the bathroom. All right? Because I wanted that water safety to be watching me. Okay? And if that water safety knew that Jim Green in this 2-hour dive is going to come out and he's going to have, or she, have the opportunity to go down and take my position, they'd be watching me. By golly, they did. So that went on for quite a while before the test conductor said, "Jim, can I see you in my office?" and said, "Well, I noticed that somewhere along the dive you get out." I said, "Yeah, it's just all that coffee I drink. I'll just have to cut back on the coffee." He says, "Yeah, okay, you do that." I never did. I never did. Yeah.
Hi. Your answer raised me another question, so I will try to summarize my questions.
Yeah.
So first question is that I assume that the suit is one size because there are one size on ISS, like of the suits. That's first question, and then it's the persons that will be able to go to the walks outside that are the ones that will fit the suit, or not, if my assumption is wrong. And also I wanted to ask, from your experience, if you think there are applications that are needed for the training and they don't have now, like how to improve the delicate motorica. I hope I said it right.
Okay.
Delicate hands work.
All right, let me see if I can tackle all those. All right, so as I mentioned, we evolved from suits that were Apollo, which were one piece, and therefore made specifically per astronaut. Okay, and so as astronauts would fly, their suits would be retired, and Marshall would go get them, some of them, and then use them in the tank. So we always had a set of Apollo suits, particularly in the late 70s and into the 80s, that were developed in the late 60s and early 70s. All right, so there always seemed to be quite a few suits there. And they'd have a suit room, they'd have everything just like they did at Kennedy. And so what they'd try to do is somebody would come in, they would size them to be, to take somebody's suit, which was as close to what they could fit as possible. A lot of the engineers that were hired to build the mock-ups would then also be in the suits, at least for the first few times, to test the mock-ups before, to make sure they were right and that things were happening before they really started conducting the entire test as they would create those. We moved then by mid-80s, maybe 84, into the shuttle suits. Those were modular. So once again, the Apollo was one piece with 2 gloves you put on and a helmet you put on. That was it. Now we move into an environment with shuttle suits where you got 2 gloves you put on, a torso, and legs, and so as modular as possible so that you actually can accommodate somebody taller or shorter. Now, what we have on station is a certain set of those things. You probably remember the time when we were thinking about having 2 women do an EVA, and then we decided we couldn't do that. Well, we couldn't do it because we didn't have all the right modular pieces for the 2 women to be comfortable in the suits. And so we brought them up. That NASA took care of that. Must have brought additional suit material up so that a month or two later, they actually we did have two women go out and do that. But the modular stuff is really great because then you can create a size that fits. Okay. And was there one other that I missed, or did that capture pretty much everything? So as I mentioned at Marshall Space Flight Center, they just had a call to the community of civil servants. They didn't go outside to look for divers to come in. So that meant I had two jobs. I worked as a scientist in a laboratory, and my supervisor would approve me taking a morning or an afternoon to go over and dive. Now that worked out great because my supervisor was a mission specialist. He was doing the same thing. He was going over and learning how to back up. He turned out to be not primary but secondary on a mission, on a real Skylab mission that would go up and they would have a module and do all kinds of stuff. And so he was learning that. So we were not only working as real scientists on data from the Science Mission Directorate, but we were working for human exploration. And to me, that was just fantastic. I loved it because I got to see what the rest of NASA was doing that the scientists only hear about, and they got to see real scientists. Okay, and that's an important mixture, to do. There's cultural changes that happen when you can put those two groups together. Okay.
All right, Jim, I think we are unfortunately at the end of our allocated time for this lecture, but what a fascinating one is that. One thing which was interesting for me to hear, actually, there were several questions about, what's the future of it, and right. you basically, said it's actually working. So, the future is, still this, but, there are interesting ideas. I think from this class, actually you can think of what is the future of, making this even more successful and for the future missions.
Hopefully this gives them enough background that, and I'll be available to talk more, and your projects will be successful.
Indeed. So, thank you very much, Jim.
You're very, very welcome. Thank you.
All right, so thank you very much, everyone, for joining us tonight. We will have indeed another distinguished lecture next week with Jim Green. But before that, actually, this week we have one final event that we will also be live streaming. Tomorrow and Thursday, you're free. There's no live stream. On Friday, until Friday, actually, our participants here, some of our participants, will be working on simulating a sample return mission on Mars with robots. Okay, they already started building their robots. They have a task to start on a base. They go around our simulation of the Mars yard, collect samples, and return them back. Okay, at 2 p.m. Portuguese time on Friday, we have 6 rovers competing to get the most samples returned back. And we will be live streaming this event. So please join us live online as well to discover which rover will indeed make it to the end with maximum sample return. Until then, thank you very much. Stay safe, stay with space. Take care.